So, how do carboxylic acid derivatives react? This is a general reaction where we are starting with the derivative of carboxylic acid. By varying Z, we can get the different derivatives of carboxylic acids to start with. So, starting with any derivative of carboxylic acid, we can do a reaction with a strong nucleophile or with a neutral weak nucleophile. Now, the mechanism is going to differ a little bit with the neutral weak nucleophile based on the medium that you are working with, either an acidic or a basic medium in there, but the product is going to be the same. If we have a strong nucleophile, the nucleophile is going to come attack the partial positive carbon. You are going to form a negative charge over here. In all the cases, Z is a very good leaving group. So each of the derivatives of the carboxylic acid will have a leaving group in there. So when you do resonance and you close back the carbonyl, the Z has to leave. So what you have done over here is that you have substituted Z by the nucleophile. There are variety of nucleophiles that we can use. The nucleophiles can vary between strong nucleophiles and the neutral nucleophiles in there. We have oxygen nucleophiles, we have nitrogen nucleophiles. And by changing the nucleophile, you can change the product that is formed. The derivatives of carboxylic acid, whether you are starting with an acid halide or an anhydride or an ester or an amide, they all work with oxygen nucleophiles and nitrogen nucleophiles. So we're going to consider the reaction of each one of the derivatives of carboxylic acid with each one of these nucleophiles. So let's go ahead and consider the reaction of alcohols. This is the neutral nucleophile with all the derivatives of carboxylic acids. Now, each of the derivatives of the carboxylic acid is going to have a leaving group. So we're going to end up having the OR of the alcohol replacing all of these leaving groups in there, and that is going to form an ester. So you're going to end up getting an ester as a product. We said that every time you have an alcohol as a nucleophile, then your product is going to be ester. Now the byproduct is going to differ based on what is leaving. So based on the type of the derivative of the carboxylic acid that you start with. So we said that acid chlorides, they are very reactive. And because they are very reactive, the reaction can happen with the neutral nucleophiles without any acidic medium to drive the reaction. In there, since the Cl is a good leaving group, the alcohol can attack the carbonyl, form a negative charge, everything closes, and the Cl is going to leave. In this case, same thing for the anhydride. Those two are reactive, although acid chloride is more reactive than the anhydride in there. So no need for the acidic medium for these two starting materials in there in order to get to the product. However, with the ester and the acid, both of these are less reactive than the acid chloride and the anhydride. So whenever you react those with alcohols, you need an acidic medium to drive the reaction to completion to get the ester. Action where you start with an ester, you react it with an alcohol in acidic medium, and you get another ester. This is called a trans esterification. This is different than what we went over earlier, which is esterification. Esterification is when you start with an acid and you react it with an alcohol to get an ester. Okay, so this is the difference between both. But both of them happen in the presence of an acidic medium. Let's start with the first case over here, the acidic chloride with the alcohol. HCl is very bad acid to form in any reaction. So this is why you need a base to trap it and prevent it from forming. This is why every time we start with acidic chloride, you're going to see that we are going to use pyridine as a base. Pyridine is used to trap the HCl. Trap it by doing what? By doing simply acid-base reaction. So this is the acidic hydrogen, this is the base. The base is going to come, take the acidic hydrogen, chlorine is going to leave. So you're going to end up getting pyridinium chloride. So it's going to prevent the HCl acid to form. And this is my target because, as I said, HCl is a very bad acid to form in any reaction. If we can trap it or prevent it from forming, then we need to do so. The reaction is going to proceed by the nucleophile attacking the carbon of the carbonyl, forming a negative charge on the oxygen. Then always remember, whenever you are starting with a derivative of carboxylic acid, you're going to end up having a leaving group. So that leaving group needs to leave by resonance. So every time the leaving group of these carboxylic acid derivatives is leaving by resonance, the lone pairs are going to close and the leaving group is going to leave. Then any extra hydrogen in the solution, because remember that your product has to be neutral. So any extra hydrogen in the solution, that is going to be picked by any base in the solution. The base over here is the Cl minus, although this one is a weak base. By the way, it is not a strong base, but it can come and pick that hydrogen in there and make an HCl. So the moment you have an HCl in there, pyridine is going to act immediately, take the acidic hydrogen and trap the HCl. This is going to be your organic product in there. We don't care about the byproduct, but I'm just showing you over here what is the role of the pyridine and why we are using the pyridine in the reaction. The reaction is going to proceed exactly the same with anhydride, and you are going to get an ester, in this case, of the carboxylic acid. So let's walk through this mechanism over here. Here I'm starting with a cyclic anhydride in there. Always locate the bond that needs to be broken. And I highlighted over here all the bonds that are going to break in the reaction. These are the bonds that connect functional groups together. These are the reactive bonds, weak bonds, and they can be broken. You have the bond between the carbonyl and the chlorine, the bond between the carbonyl and the oxygen. This is the ester bond over there, and the bond between the carbonyl and the OH. All of those bonds are going to be broken throughout the mechanism of the reaction. So highlight the bond that you are going to break, and then always look at the medium that you are working with over here and check. Are we using an acidic medium or a basic medium? If you have nothing in there, then this is going to proceed by a basic medium. So this means that the nucleophile can immediately come and attack the carbon of the carbonyl. Okay? So it's going to come immediately. It's going to attack the carbon of the carbonyl, form a negative charge on the oxygen. As I said, every time you form a negative charge on the oxygen, resonance is going to happen to break that weak bond. So resonance is going to happen, and we are going to break this bond over here. Notice what I did. I added this whole thing together with its hydrogen. So you would need to form an O plus a charge and 3 bonds around the oxygen. Make sure that you write your charges and write them right, please. When oxygen has 3 bonds and a lone pair, it is a positive charge. When oxygen has 1 bond and 3 lone pairs, it's a negative charge. Resonance happens and you are going to break this bond, form a negative charge on this oxygen in there. Then you're going to end up having a hydrogen shift or a proton transfer. so that you will form a neutral product. This is what you need, a neutral product. So notice here when I broke this bond, I added the alcohol to this carbonyl to make the ester. So the ester is made on this carbonyl over here. This is going to be the ester part in there. And whatever broke is released in a form of an O negative, and that O negative is going to pick any extra hydrogen in the structure in there, becomes protonated, and turns into an acid. After all, if you look at the anhydride, if you start with an anhydride, you react it with the alcohol, your byproduct is always a carboxylic acid. But the difference in our example is that I'm starting now with a cyclic anhydride. Cyclic anhydride means that those two are going to be connected with each other. And this is what I have over here. They are connected with each other. So I'm going to form the ester and the carboxylic acid in one molecule. Let's do an example on the trans-esterification. So we said that trans-esterification is whenever you start with an ester, you react it with another ester, but now the medium is acidic. It has to be acidic. Whenever I talk about esterification, the medium needs to be acidic. It goes way faster in order to get to the ester. So over here, I'm expecting to get an ester in this case. And to get an ester, I would need to lose the OR from the first ester and the hydrogen from the alcohol. Always the alcohol loses a hydrogen. The alcohol cannot lose an OH, as we mentioned last time. Because if the alcohol loses an OH, then you're going to end up having a carbon standing alone. And this cannot happen. So you're going to end up getting an alcohol as a byproduct and an ester. Esters are not very reactive. This is why we are using a catalyst, which is the acidic hydrogen. So the reaction is going to happen in acidic medium as usual. Acidic medium, the first step, you are protonating this oxygen so that you can make this carbon over here. You want to make this carbon very partial positive. And to make the sp2 carbon very partial positive, you have to introduce an oxygen with a positive charge in there so that you can have more pull of electrons towards the oxygen. That's going to leave this carbon in desperate need of electrons. So the nucleophile is going to come, it's going to attack, form a lone pair on the oxygen. Now I want to break this bond over here. I want this to leave. So what I need is to break this bond. But the rule says that in acidic medium, the oxygen cannot leave in a form of a lone pair. You need to protonate the oxygen in order to allow it to leave. So the oxygen needs to have a positive charge on it in acidic medium for it to leave. So once the alcohol adds up to the carbonyl in there, you will have an extra hydrogen in there, which is on the oxygen. It's this extra hydrogen. So you can simply do a proton transfer in order to allow this oxygen over here to be a positive charge. So now once it's a positive charge, now you can do resonance and the whole thing is going to leave. So see what I did? Oxygen here, the OR cannot leave in a form of a lone pair in acidic medium. So I have to make it a plus charge so that it can leave. And it can leave by a simple resonance in there. Any acidic hydrogen in the product that is going to be picked by any conjugate base in the solution, and you are going to end up getting the ester product.